Hello everyone and welcome back to another episode of Power Logic. So today we are going to be going over the 2022 Aime Ii problem 9. That line A and line B be two distinct parallel lines for positive integers m and n, distinct points a1, a2, to am lie on line A, and distinct points b1, b2, b3, bn lie on line 2. Additionally, when segments a sub I, b sub j are drawn for all I equals to 1, 2, 3, to m, and j is equal to 1, 2, 3, to n, no point strictly between line A and line B lies on more than two of the segments. Find the number of unbounded regions. Find the number of bounded regions into which this figure divides the plane when m is equal to 7 and n is equal to 5. This figure shows that there are 8 regions when m is equal to 3 and n is equal to 2. So I believe that a lot of people would be probably scared off to this problem because this problem looks kind of abstract since you're dealing with a lot of intersections and you only bound the region by the intersections, which can actually work well when the case is small, like 3 and 2, but when the case is 7 and 5, then it becomes really hard. Now this problem would kind of encourage us to first try to find some patterns, if it's possible. So let's start with the two lines. So what is the case when m is equal to 3 and n is equal to 3? Excuse me, let me just make my line. Now when n is equal to 2 and m is equal to 2. Now the 4 lines are just going to be these. And this clearly just bounded 4 regions. 1, 2, 4. Now what about the case when m is equal to 2 and n is equal to 3, which we just given? But this kind of encourages us to kind of try to think this problem recursively. So now how does 2 and 2 get to 2 and 3? So now we just draw the 2 and 2 case. Then this one has 4. Now for 2 and 3, because we know that if we change, so m and n and n and m actually yields the same result, despite of the order when one is up and one is down. So basically, without loss of generality, we're just going to make one more point onto the bottom. Now there are only two lines that's going to be added here. What are the 2 lines? From this point to the number of points on the top. So there are 2 lines. Now let's say we have a region, like something like this. Then this one is a 1 region. Now I claim that any intersection, that any line that enters this region and exits this region will actually create 1 more region. So you can try any lines. This will always create 2 regions. It will never create 3 regions. And this identity would be really easy to prove. So now from this claim, now we just want to focus on these two lines, since without these two lines, then the region will not change. So now let me just zoom in this diagram. So now we're going to focus on this line right here. So this line intersects this line and this line. And we also have this line, which the other blue line, which creates a new region, right? This part. So now let's think about the condition in which two lines will intersect in such diagram with M and N. So let's say if we define a line which starts at P and ends at Q to be like such a line. So for PQ, let's say G of PQ is going to be, we define G of PQ to be the number of intersections. Then we consider G of PQ, then in order for it to intersect, we must have a line called XY such that one of the two conditions satisfies. The first condition is we either have P is less than X and Q is greater than Y, or P is greater than X and Q is less than Y. So you must have one of the conditions to satisfy, right? Because imagine if we have both that are less than P and Q, or both that are greater than P and Q, then we're going to have some line like this, which obviously will not intersect between these two lines, since we know that every such line segment starts in one of the vertices and ends at one of the vertex. So, okay. So now we know that f of 3, 3. Let's call f of 2, 3. Let's call f of m, n to be the such number of intersections. Then f of 3, 3. No, 2, 3. So f of 2, 3 is equal to 8. Now, how does it go from f of 2, 2? So basically, for this line, we're going to create a new region, and then this line will also split the new region. So we're going to have m more regions, which m stands for the number of points on the top line. Now, for this line over here, we're going to intersect So for this line here, we can actually choose m minus 1 points on the top. Well, because we must have like the second condition when, let's say this is Q and this is P. Since Q is the rightmost point, we must have the bottom point to be less than Q, while the top point to be greater than Q. So therefore, we only have m minus 1 choices for the top point, if P is the leftmost point and Q is the rightmost point on the bottom, since we defined Q. Now as we push it rightward, then the number of choices of the top point would always decrease by 1 until it becomes 1, while the number of choices for the bottom will not change since it's fixed. So yeah, we can actually make a recursion right here. So from what we have gotten so far, then f of m is actually equal to f of m n minus 1. Now, plus, so f of n minus 1. Now, plus m, right? Since we have m points on the top. So in here, we're going to have f of 2, 3 is equal to f of 2, 2. Now we're going to plus a and m. Now for the bottom, we're always going to have n minus 1 choices. So n minus 1 times, well, from here we can see that we have m minus 1 choices for the top, and we add it all the way to 1. So this is in fact just an arithmetic series. Now we're going to simplify this a little bit. Now this one, you can notice that it's just equal to m choose 2. Now this actually is the same if we swap m and n. It can also be written as f of m minus 1 n plus n plus m minus 1 times n choose 2. So now we have this recursion, we can just bash out the table, and what we want to find is essentially f of 7, 5. So now first we're going to start with f of, so f of 2, 2 is equal to 4. Now f of 3, 2 is equal to 8. Now f of 3, 3 is equal to 8 plus a plus 3 and then plus m minus 1. So plus 2 times 3 choose 2, which is equal to 17. So just going to brute force. It's equal to 17 plus 17 plus 3 plus 3 times 3 choose 3, and 3 times 3 choose 2, which is 29. Now f of 5, 3 is just equal to 29 plus 3 plus 4 times 3 choose 2 is equal to 44. F of 6, 3 is equal to 44 plus 3 plus 5 times 3 choose 2, and this gives us 62. Now f of 7, 3 is equal to 62 plus 3 plus 6 times 3 choose 2. And this actually gives us 83. So we're just going to continue our table. Now f of 7, 4 is equal to 83 plus, well, keep in mind, we want 7. And then plus 3 times 7 choose 2. So this is equal to 150. 153. Now, finally, f of 7, 5. 153 plus 7 plus 3 times 4 times 7 choose 2, which is equal to 160 plus 4 times 21, which is equal to 244. And that is essentially our answer to this problem. Thank you for watching. Hope you enjoyed, and I will see you in the next video.